All right, so today we're going to continue with basic tree traversal algorithms, and then we're going to introduce even more structure. Remember, we start out with general graphs, and then we add structure, add structure, add structure to restrict them more and more so that we can exploit that structure for efficient operations. Remember that we are online. If you have any questions, go ahead and post to Piazza. All right. So we left off last time by looking at preorder traversal. And we actually implemented this, right? That means that you go in a root left-right manner. The other two traversal algorithms or strategies is that you explore the left subtree first, then the node, then you go to the right subtree. Or that's in-order traversal. Or a post-order traversal where you completely explore the right subtree, left subtree, completely explore the right subtree, and then finally the node at the end. I want to go through an example of both of these, and then we'll go ahead and go through a quick implementation of them both, okay? So here's the same tree as before. Let's go ahead and do an in-order traversal. Now remember that an in-order traversal means that you're going to go to the left, then you're going to do the root, and then you're going to go to the right, and of course that is a recursive strategy there. Right? The implementation may or may not be recursive. It could be stack-based or it could be something else entirely. We'll get to that when we get there. Okay. So, what is the first thing to get enumerated? We come into A. Right? Do we immediately say A? Nope. We go to the left subtree before coming back and processing A. All right, so now I'm at this right subtree rooted at B. Do I immediately process B? Nope. I go to the left subtree again, and it again, and it again, and it again. And at this point, when I'm at L, there is no left subtree to process. So what ends up getting processed first? L. And I am done with that node. Now, what I'm going to do is I'm going to come back up from the recursion after I've processed this entire left subtree, which happens to only be one node. And now I process G. And then I go on to process the right subtree here. Right? So G, and it's been processed. Now I'm at my right subtree rooted at M. But do I immediately do M? Nope, I do the left subtree, which is going to be R, and then that's a seed. It's only one element. So we end up processing R. We then come back up and process M. Right. Fast forward a little bit, now we can go a little bit faster here. Realizing that we've done the left subtree here hanging off of D. What comes next? D. And then we process the right subtree. The right subtree is going to be what? Just looking at this entire right subtree here, what's the order? We process the left subtree, which doesn't exist. Then we process the node, the root, and then we process the right subtree. So, H, N. And that's done. At this point, the entire right subtree hanging off of B is processed. And so we process B, and then go to the right subtree. Just looking at this tree right here, tell me what order I'm going to do stuff in. No left, so I go E, then O, then I. E, O, I. And those are all done. At that point, I'm done with the entire left subtree hanging off of A. Okay? And that's when I do A. Okay? I'm going to go down to the next line because I'm running out of room here. But at this point, A has been processed, and then I take care of this left subtree. There is no left subtree hanging off of C, so fast forward here a little bit, double time it. C, then what? P, J, Q, F, after I'm done with this subtree hanging off of this here, and then K, and I'm done. Right. What can you observe about this, this ordering? Where does A, the root of the entire tree, fall? In the middle, right? Whatever that means. What that means in this case is that everything to the left of A is in the left subtree, everything to the right of A is in the right subtree, right? Just as we would expect with an in-order traversal, okay? Let me go ahead and create a new version so that we can, Crossy Road, yes. Nope, that's not what I want, sorry. Not yet, at least. Insert from, the same binary tree as before. There we go. Okay. Now let's do a post-order traversal. Remember that a post-order traversal is going to go and save the root for last. It's going to go left, then right, and then finally the root at the end. So immediately, what should you expect at the end of this processing? What's the very last one going to be? A, right? Because that's the root of the tree. Okay? But let's not jump to the end. Let's actually do this. Okay? What order? What's the very first thing that gets enumerated? I go left, 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 left. Right? L. Well, that'll end up being the first thing, but only because it has no children, right? I would have done its left child first, then its right child, and then L. Good. Now do I do G? Nope. I wait until I'm done with the right subtree. Once I'm at M, though, do I process M? No. I do the left subtree, R, the right subtree, which doesn't exist, and then M. So, R, M. Only after both the left subtree and the right subtree are done do I end up doing G. Okay? Next. And here we can go a little bit faster. Then H, then N. N, good. Why? No child, right child, then H. Right? So N, H, and then back up to D after I'm done with its right subtree, right? I ended up doing N and H, and then I'm done with its left subtree, I'm done with its right subtree, so I end up doing D. What's next? B? Nope, I have to do B's right subtree before I consider it. So E, there's no left subtree. I hold off on E. I go to its right subtree. I have a left subtree and a right subtree, so it's going to end up being O. There is no right subtree, excuse me. Then I. And then after I'm done with that, E and B. Right? O, there is nothing over here. I already would have explored the left subtree over here. E, and then finally, because B and E are done, now you do B. Okay? There. What's next? Yeah, you look at C, no left subtree, so I go to the right subtree. I'm at F, I do the left subtree, then the right subtree, then F. So I'm at the left subtree here, and this is just a perfectly formulated 3-node tree, so what's it going to be? P, Q, J. So P, Q, J. That takes care of F's left subtree. Then I do K, its right subtree. And then finally, after I'm done with that, then I can do F. Okay? Then it's all just unrolling all the way back up to the top. C and A. Good. So, let's program it. All right. What I'm going to do is I'm going to show you the recursive versions. Right? Remember that we did this recursive pre-order traversal, right? And I'll call it recursive in-order traversal. And then, of course, I've got this other recursive pre-order traversal. That was just my setup, right? And this will end up being in-order traversal. There we go. How is it going to differ, though? So this entry point, that doesn't differ at all. I'm just setting up this, this list of results, and then I'm starting at the root, and I'm passing on that list. Preorder, I just copy-pasted this from preorder traversal. We process U, then we recurse left, then we recurse right. So what's the only difference with an in-order traversal? Again, this is a pre-order traversal here. What do I do? Right. Or correct, not right. All I do is move where I process it into the middle. Right? So, 2, 1, 3. I'm going to keep those numbering there. And then, of course, also I need to call the right recursive methods there. Right? Let's change the toString method so that it uses that recursive in-order traversal. Right? And let's see if we come up with the same solution that we just did by hand. LGR, remember that this is an in-order traversal, LGR, MDHN, MDHN, BEOI, blah, 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 blah. A is right in the middle, QFK. I'm convinced. Right? Excellent. All it took was moving one line of code to another part. Let's do a recursive post-order traversal. And so there's my entry point there. And I will, of course, need that, that function. So here is, I'm just copy-pasting the in-order traversal, and I'm changing it to a post-order traversal. Change those function names. Right? But now what's the difference here? I went left, right, I went left, process, right for an in-order traversal. For a post-order traversal, where would I end up processing? At the end. That's the only difference when you process something. And I get LRMGN, LRMGN, HDOI, blah, blah, blah. I'm convinced that it's correct. Right? Now you might be asking yourself, oh, okay, wow. You know, that's a really powerful argument for recursion there. All I have to do is swap one line of code, and I get something completely different. Right? Same argument can be applied to non-recursive code. Right? I can swap a data structure and get a completely different ordering. What might it look like if we did decide to do a non-recursive solution? I'm not going to go over that in detail, but I do have archives showing a Java implementation of it. And of course, in the book, we've got this nice stack-based in-order tree traversal. We also have a nice stack-based post-order traversal. Right? Now, I'm not going to go through every single line of pseudocode here. What I'm going to do is I'm going to show you the idea. Right? So how would you go about doing any of this stuff? All you need to do to know the difference between those three orderings is use the same exact stack in the same exact manner. It's just that you need to keep track of a little bit more information. Suppose that I'm at a node U. Well, obviously I got here somehow. I could have come from the parent, or I could be returning from a recursive call from the left child, or I could be returning from a recursive call from the right child. Right? All I need to do is to distinguish which one is the case. Right? If you came from the parent, where do I go to next? Go to, so if you came from the parent, go to something, and process if ... Right? So I'm coming from the parent, okay? Where do I need to go to next? And it doesn't matter what traversal strategy, pre-order, in-order, or post-order. I mean, it matters when I process this thing, right? Where am I going to next if I came from the parent? To the left, right? Go to the left. And we'll hold off on, do we process it now? I don't know. Let's hold off on that. If I came from the left, right? The idea is that I'm returning from a recursive call down to the left subtree. Where do I go next? I go right. If I'm coming from the right, that is, I am returning from basically a recursive call to the processing the right subtree. Where do I go next? Back up to the parent. Right? Now, let's understand what we have to do to actually produce an in-order, post-order, or pre-order traversal. If I'm coming from the parent, as in this first scenario, I need to go left next. If I want to process it right now, what kind of a strategy is that? That's a pre-order traversal. Process if pre-order. Now, there's the second scenario. I'm coming from the left, returning from the left subtree. If I process it now, before I go on to the right subtree, which process order do I have? In order. And by process of elimination here, post order. Right? Again, the idea is that you're coming back from the right, having gone low right, and then you're returning back up here, so go ahead and process it. Right? Think about this in terms of the actual tree. Let's go ahead and get that tree back here, over here. There we go. What you're doing is think about these edges as walls. All you're doing is you're walking around the perimeter of these walls. I'm starting at the top and I'm coming down to the left child. Then the left child, left child, left child, right? And then there is no left child, there is no right child. So what do? I come back up. And then I go back down, left, come back up. Right? And here I'm just going to draw it as one smooth line. Right? All you're doing is a perimeter walk around this entire tree. And depending on where which direction you're going, are you going back up or are you coming back down? That all determines whether or not you're doing an in-order traversal, post-order traversal, or pre-order traversal. In fact, you don't even need to keep track of all the stack nodes, or you don't even need a stack, is what I'm trying to say. All you need to know is what? Where you are and where you came from. All you need is a previous node and a current node in order to do these three simple rules right here. Right? You don't even need a stack at the end of the day. You certainly don't need recursion. You just have to keep track of where you've been and where you're going. Right? And what kind of process order you want. I'm going to show you yet one more processing order. Right? All three of the process orders that I just showed you are variations on what's called depth-first search. Right? Depth-first search is where you have a graph and you go as deep as possible as you can. Right? Depth-first search is kind of like searching a maze. You, again, you start at that point and then you go as deep into the maze as you can. When you hit a dead end, then you start backtracking. Right? Not all searches are like that. Some searches are, for example, missing persons. You go to the place that you last saw them, and then what do? Do you go off 10 miles in that direction searching for them? No. What do? You check around, right? You set up a search perimeter of maybe 50 feet, right? Okay, I didn't find them there. Let's go ahead and expand our search perimeter, or search circumference, or whatever you want to call it, so that we're looking for them through in a radius of 100 feet, right? And then you do that again and do that again until you find them, or the area has become so big that it's no longer feasible to do so, right? That's the idea behind breadth-first search. Breadth-first search with an oriented tree looks something like this. You start at the root, of course, because that's where all searches start with trees. And what you do is you check everything that is a distance 2 away from the root. Then you check everything that is a distance 1. Now you do everything that's a distance 2 from the root. Then you do everything that's a distance 3 from the root. Then 4, and then 5, until you're done. Right? Or put it another way, instead of thinking of it as a perimeter and distance, since we've already drawn it as an oriented tree with levels, you start at the top, right, and you go left to right. ... Then you start at the second level, go left to right. ... Third level, fourth level, fifth level, and sixth level. right? If you want to, depending on where you start your counting, right? And all you're doing is, going back to the other line. That's how you read, right? Left to right, top to bottom. How might we achieve this idea, right? So let me go ahead and get rid of all my scribbles. All right. So let's make it a little bit smaller now. This is called a breadth first search. Search things that are close first. Search things that are a distance 1 away. Then search things that are a distance 2 away. Distance being the length of the path from the root to any other node. Okay? Obviously, what's going to be my order here? Alphabetic, because that's the way that I wrote it, right? Naturally, if you're going to draw a tree and label them A, B, C, D, E, F, G, you can't escape it. You're going to label it top to bottom, left to right. But how do we go about computing them, right? Because a computer doesn't see this way. The computer doesn't see this oriented tree. It just sees a bunch of memory, right? So I'm going to draw you a picture here. I'm going to start at A. So I'm going to put A over here, right? And then I'm going to take it out and process it. After, before, during, whatever you want to, however you want to think about it, what I'm going to do is I'm going to want to set it up so that I go B, C next. So what do I need to do? I need to put B and C into the same data structure. B, C. Right? Process A. That sets me up for my next iteration. What do I pull out next? B, but what have I saved? C for later processing. I do the same thing. I take care of B's left child and I take care of B's right child by putting them in this thing over here, this data structure, D and E. Right? And then I process B. Right? And it's kind of boring, A, B, C, D, E, F, blah, 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 blah. Right? I pull out C, which is at the previous level, and I push its, or I take care of its left child, and I take care of its right child. Well, there is no left child, and so I will put F into this, and you can start seeing the pattern. What is this thing right here that I'm using? Is it a stack? It's a queue, because I'm putting stuff in at one end and pulling them out at the other end, and you can imagine what this queue is going to look like, right? It's A, B, C, D, E, F, G, right? Same way as when it's coming out of this. Right? What were the steps that I did there? Starting at the root, you enqueue the root, so that's in there. But now let's think of this while loop. While the queue is not empty, what do? I pull something out, so X will end up being Q.DQ. Right? I process it, and here it doesn't matter if you process it before you take care of the children or take care of the children and then process it, because it's all going to be the same order. But I go left to right to get this visualization right here. If you wanted to go right to left, that's fine too. It'll just be a different order, right? So process X, NQ, X's left child, and then NQ, X's right child. Okay. What would this look like? Let's actually go ahead and implement this. Right? So, same idea here. We will return a list of those elements. It's not going to be recursive. It's going to be a BFS, breadth first search. Breadth first search. Okay. What's it going to look like? First of all, I need a queue, right? So I'm going to use a deck, right? D, because I think that's what we used before, right? Yeah. I'm just going to grab this. Right? There we go. In fact, I'm going to grab all of this because that's some boilerplate right there taking care of an empty tree. Right, there we go. All right, what's my first step? I'm going to go ahead and go with I'm going to NQ. So let me not call it S anymore. What should I call it? Q, because it's representing a Q now. Q dot NQ. What is it? Add last. Right? And this dot root. So last is going to be my insertion point. If last is my insertion point, then my exit point is going to be first. Right? So while the Q is not empty, Q dot is empty, while it's not empty, I will pull something out. So tree node T X, I'll even use the same variable name that I used over here, X, right? Is equal to Q dot get first. There we go. Again, if I just have to be consistent about it. Take your Q and move it around, and now you're working at the other ends, right? And then process it. So processing it means simply just result.add x.getValue. And then I need to take care of the left child, then the right child. So Q dot add last, x dot get left child, and then Q dot add last, x dot get right child. There. Let's go ahead and test this before we make some observations. Again, what should I expect? A, B, C, D, E, F, G, H. Okay. It should be remove first, I think, because this is just a peek operation. Remove first. There we go. That's all I need. Yeah. There we go. Oops. Darn it. No pointer. Oh, you know what? Yeah, it might not have a left or right child, so technically we have to do this. If x dot has left child, only then would you actually NQ it. If x dot has right child, only then would you actually NQ it. There we go. And now I would expect A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R. Done. Right. Compare and contrast this here. Take a look at this code right here, and take a look at our preorder traversal code. Now, I could put them, you know what, here, let me go ahead and compare with, where is compare with? Okay, it's not going to let me do that, so I'm going to make a copy of this really quick. Okay, and then select them both, compare with each other. Okay, so here on the left-hand side, let me go ahead and display the breadth first search. Here on the, I don't want to, yeah, okay, which one's number 2? This one. Let's go ahead and get rid of everything except for, where was it? Here we go. There. I'll get rid of this too, just for a second. All right, and then make everything match up there. All right. So, what noticeable differences do you see here? It's not going to be perfect, but one, I've got a queue instead of a stack. But otherwise, push something, add last. While it's not empty, you remove it, you process it, right? That's what I did right here. And then you go left and then go right. Here I went right and then I went left. Right? Is there really any substantive difference between these two pieces of code? Not really, right? It's the order of left-right a little bit, but it's the data structure, right? This all goes back to the very beginning, right? Smart data structures and dumb code are a lot better than the other way around. This is dumb code. Put stuff in, take stuff out. Put stuff in, take stuff out. The real power is in the data structure. A stack gives you one way of doing things, preorder traversal. A queue gives you a completely different way of doing things, a breadth first search. Right? All I had to do was swap out the data structure, and it took care of all that for me. Right? Awesome. Okay. All right. I will, don't save. Don't save. Okay, there we go. And then I can go ahead and get rid of this. Delete. There we go. All right. Questions so far? No? Then, now that we've got a traversal strategy, let's go ahead and add some more structure so that we can start exploiting that structure. And that's going to end up giving us what's called a binary search tree. Right? A binary search tree is a binary tree, so it's still a binary tree, and what we've talked about up to this point, such that every node U holds a key K, such that every node in the left subtree is less than K, every node in the right subtree is greater than K. Now note here that I'm emphasizing the words every, right? That has to hold inductively or recursively for all subnodes, okay? So let's go ahead and take a look at an example over here. Once I bring it back up. There we go. There. There's my binary search tree. Now here I'm just using integers, and it's sufficient to use integers because ultimately you're probably going to be using some sort of hash code, which takes an object state, its strings, its lists, its floating point numbers or whatever, and produces just one number, an integer number, right? And so it's enough to use that as the key for all of your stuff that's being stored in your data structure. Now, let's make the observation. At the root here, we have 50. Look at everything in the left subtree here, and it is less than 50. Look at everything over here in the right subtree, and it is greater than 50. What would happen if I had two 50s? I would just have to pick a lane, right? Everything less than or equal to goes over here, right? Or everything greater than or equal to goes over here. But you can't have it both ways, right? It has to be less than over here and then greater than or equal to over here, or less than or equal to and then greater than over here. Because if you want to look for that duplicate 50, is it in the left subtree or is it in the right subtree? Both. You don't want that, okay? Look at the inductive property here. That means that it holds for everything below. 40 is my root for this left subtree. Everything over here in the left subtree of 40 is less than 40. Everything over here in the right subtree that is greater than 40. Right? That holds for every single node in this entire tree. And that's called a binary search tree. Why is this nice? If we've got this structure, what can we now do? Think of our three basic operations. One basic operation is search. We want to search for a particular node. Right? Let me come back over here to our example, and let's search for, say, 24. Right? How would I end up doing this? Start at the root. 24 is less than 50. So it's first of all, it's not equal to 50. So that's not the thing I'm looking for. So the thing I'm looking for is less than 50. Where do I go? Into the left subtree. I'm now at 40. 40 is greater than 24. So if 24 exists, where should it be? In the left subtree or the right subtree? Left. 20 is not the thing I'm looking for. 24 is greater than 20, so if it lies in this tree, where should it be? Right? And I end up making, 24, I found it. I ended up making 1, 2, 3, 4 comparisons to find what I was looking for. Right? Sometimes you might get lucky. What about a search for 50? How many comparisons do you need to find what you're looking for right at the root? Just one. Let's search for 42. Okay. Again, I'll start at 50. 42 is less than 50, so I go over here. 42 is greater than 40, so I would go over here. 42 is less than 45, so I end up over here. Oh, what happened? There is nothing there. I did 1, 2, 3 comparisons and then comparison to null at the end here to see that there is no such element. Once you've fallen off the edge of a tree, right, then you can say with absolute certainty, as long as this binary search tree property holds, is that the 42 does not exist. Which element could I search for in this tree to maximize the number of comparisons? 12, right? So let's search for 12. I'll start at the root, go left. So 1, 2, go left, 3, go left, 4, go right, 5, go left, 6. Right? What does that correspond to? The depth. So searches are at most. What's the depth of this tree? Let's get technical here. 1, 2, 3, 4, 5. Right? Searches are at most D plus 1 comparisons. But guess what? Forget about that D plus 1. Order D. Now let's go back. What observation did we make about a tree that is full? Recall. A full tree with n nodes has depth, what? Log n. So if searches are order D and it's full, then searches are order log n. And we've achieved one of our goals, right? And I'll show you how to do the other operations here in a second. Can we assume this, though? Here's a binary search tree. Oops. 100. Give myself some more room here. Sorry. 100. 90. 80. 70. ... I'll go all the way down to 10. 10 elements there. What's its depth? 9, right? Depth. In this particular case, it's 9, right? So you could have a binary search tree, BST, such that the depth is going to be n minus 1. In other words, the depth is going to be order n. It's not really a tree the way that I drew it. What is it? It's a what? It's a linked list. Exactly. It's like if you have a tree and then you prune until you have just one stick, right? It's a stick. So a linked list is a tree. It's just a stick. That's the idea. To solve that problem would require more than we're going to go over in this course. You would need a balanced binary search tree. One that restructured itself when it got too balanced to one direction. So for example, let me go ahead and just give you a preview of, this is what you usually cover in say 310, Computer Science 3, something like that. Say that I've got 30, 20, and 10. A simple 3-node tree. It's really unbalanced though. It's unbalanced all the way to the left. Right? What could I do? I could imagine that this is indeed a chain, right? Or like a linked list. And this is at the top of the hill. And so here's me. I will pull the chain and go down over to the other side of the hill. Right? What will I end up with? 20 at the top, 30, and 10. Oops, 10. Well, you get the idea. Guess what? It's balanced now. Is it still a binary search tree? Yeah. Right? Now it might involve some swinging, taking some nodes and reconfiguring them in some ways, but this is the basic idea, right? This is the basic idea. These are called rotations. This is, say, done in an AVL tree or a red-black tree. Right? There are about a dozen or so balanced binary search tree implementations that would guarantee you that the depth is going to be logarithmic, meaning that the search is just as performant as binary search is on an array-based list. Awesome. What about the other two operations, though? Whereas binary search is only good for searches on a sorted array, is our binary search trees, do they give us everything that we wanted? Do they give us efficient searching? Do they give us efficient insertion? Do they give us efficient deletion? Right. Let's find out now. Binary search tree. There we go. So we know how to search it. Do we know how to insert? All right. That thing that I did before, we didn't find 42. Insert 42. All right. Well, remember our search, right? We went this way, and oh, well, it's not here. Guess what? We put it there, right? Good. All right. What about 55? So I start at the root. 55 is greater than 50. So I come down over here, 60. 55 is less. And guess what? There's room for it. Right? So 50. Or sorry, 55 is what I wanted. Right? So we know how to insert too. All we have to do is search for where it would be. If it's there and you don't allow duplicates, just don't allow it, right? Throw an exception, no operation, return false, whatever you're going to do, right? But if certainly, if you don't find it, then there will be room enough hanging off of that node to insert it as a new child, right? It's not always going to be a leaf, all right? 45 was not a leaf. 45 had a right child. It simply needs a left child. It didn't have a left child here, so there was room for it. Right? Otherwise, it would be there. Right? You're never going to run into a collision where something is already there, right? Because if something were already there, then that thing that you are trying to insert would already be there. Right? Excellent. So you always insert as a leaf, right? By searching for where it should be. Now, once you've searched for where it should be, then it's just simply a matter of changing a bunch of nodes, right? My left child is now new node, my parent's left child is now me, and my parent is now that parent, right? So it's just a couple of pointer reference exchanges. In other words, it's still going to be ordered D, because you do have to search for it. Okay. What about deletions? Oops. So same thing to start out with, right? Search for it. So let me go ahead and move this. All right. So let's go ahead and delete 75. All right. So search for it. If you don't find it, throw an exception, no operation, return false, whatever. Right? Yeah, no operation. It wasn't there. Right? Otherwise, you search for it, and so once you've searched for it, you've come down here. Right? How do I delete this node? How do you cut off a leaf on a tree? Yeah, you just delete it. You set the parent's child reference. You do have to know, am I a left child or a right child? You set the parent's child reference to null. Right? Now, if you are a left child, like 75 is, then you'd go up to the parent and say, parent.leftChild equals null. Otherwise, if you were deleting 85, you're a right child, and so you need to understand, am I a right child? Okay, go up to the parent and delete the right child. Okay? Let's try something harder. Let's delete 49. So same thing, you have to find it. There's the thing we're looking for. Okay? How do I delete 49 now? If there are a whole bunch of things hanging off of it, I certainly don't want to throw out the baby with the bathwater. Yeah, what am I going to do? Take this and promote it up. Right? Because all you have to do is think about this. This is just a line, right? If I were to just look at this locally, that's a linked list, right? How do I delete it? Get rid of that and make these two things connected. Right? So what would it look like? I can't delete an image, but I could white it out. So, oops. There we go. And not 49, but now it's 48. Oh, good notes hacks. Okay. Let's try something even harder. Let's delete 50. Good. So, got to find it first. Got lucky. It's right there. I've got 2 children. Can I just move one up? Well, in this particular case, I could get away with it with 60. But what if there was stuff hanging off of it? What if there was, remember we put in 55? Right? Now can I just simply get rid of 50 and bring 60 up? It would have 4 children. It would have 20, 45, 55, or sorry, 3 children. It would have, if I brought 60 up, it'd have 40, 55, and 90. And is that a binary tree? Nope. Okay. Can I bring 40 up? No, same problem on the other side. So let me go ahead and reverse all of this stuff. Okay. Delete 50. Well, I know how to delete if there are no children, right? That's easy. I know how to delete if there's only one child. So why don't I take that idea and go with it? Let's go ahead and get rid of 50 here. What's one thing that I could put in its place that I know that I can delete it because it only has one child or or no children, and at the same time preserve a binary search tree property? Look at everything in this tree. What could I put up here? Could I put 20? If I put 20 up here, is that a binary search tree? Nope. Because 40 is greater than it. Could I put 28? 28 is a leaf, right? If I put 28 up here, same problem. What among these could I put up here and not violate the binary search tree property? 48? Oh, why 48? 48 would violate it? How? 49. Right? But would 49 violate it? Okay. Let's put 49 up there. Now, in order to get rid of 49, I would have to delete it, right? And so I know how to do that because we already did that over here. Right? It only has one child. And what does it look like after this? 48. And then this is gone. That's a binary search tree, isn't it? Tell me about 49. Let me go ahead and, I'm just going to go ahead and reverse this entire process here. Right? What is it about 49 that allowed me to do that? It's the rightmost in the left tree. Another way of saying that is, it's the maximum of the minimum, right? It's the maximum value of things that are less than 50. What if I wanted a candidate over here? What could I take over here and put it up here after 50 is gone and still satisfy the binary search tree property? 60. Characterize that. That's the minimum in the right subtree, right? Or the leftmost thing, and there is no left child here, so it is the leftmost thing technically in the right tree. Right? Oh yeah, if 55 were still there, then we would take that instead, right? So it seems like we've got a strategy. Can this strategy fail? In other words, I will replace the node with node u with the min value in u's left tree, or sorry, right tree, or the max value in u's left tree. Right? Either one will work. Are we going to run into a problem though? This works if if it doesn't have any children, because we know how to do that. It works if we have one child, because we know how to do that. But will it work if it has two children? So here's u, and I want to replace it. And dot, dot, dot. Let's go ahead and go with the maximum value in its left subtree. So in other words, I would go to the left subtree, and then I would go all the way to the right subtree here and get the rightmost thing. Right? Let's zoom in on that now. Say that that's the max, right? M. And suppose that it has two children, L and R. How do we deal with that? So tell me about R. Exactly. By definition of binary search tree, R is greater than M. M was not the maximum. Remember, rightmost, rightmost, rightmost. Once you get to the rightmost, what does it look like? Exactly. It might have a left child hanging off of it, and might have an entire tree hanging off of it. But if there's another element over here, then that's even greater. Keep going. Right? Likewise, the mirror image argument for your other choice. Right? So by definition, the maximum in the left subtree or the minimum in the right subtree necessarily has at most one child. And we know how to deal with that. Right? Awesome. It, of course, involves finding it. Oops, that's not what I meant. Of course, it involves finding it, which is going to be order D. Right? Plus, this is search for the thing that you want to delete. Finding the minimum, finding the maximum in the other subtree. That's at most what? Just go to the left subtree, go right, 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 right. Go to the right subtree, go left, 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 left. Right? That's going to be order D at most to find the min max. Right? And then plus order 1 to shift around a bunch of references and values. Okay? To shift references. Say what? Yep. Oh, that's actually order 1. Right? Make that thing point to that thing, make that thing point to that thing. Right? Oh, yeah. Oh, so, yes, good observation. Everything is order D. Because order D plus order D is order 2D. Guess what happens to that 2? Goes away. Okay. Well, with the remainder of our time here, let's try doing this. What would it look like? Man, I wrote a lot of stuff here for binary tree. It seems like it would be very, very useful. So I can cut and paste, or I could rename this to be binary search tree. Let's think OOP. Is a binary tree a binary search tree? Not necessarily. Is a binary search tree a binary tree? That's how we defined it. A binary search tree is a binary tree. So what kind of tool can we use here? Inheritance. Let's create a new binary search tree. And it's parameterized. And its superclass is a binary tree. All that stuff, all that work that I just put in, I now inherit it. I can do a BFS, I can do a preorder traversal, I can do a postorder traversal, I can do an inorder traversal. Why would an inorder traversal be super nice? Let me go back here and bring in that binary search tree. Do an inorder traversal here. I do everything in the left subtree, then I do this, then I do everything in the right subtree. It would be what? What's the first element? 2. Right? And then I've done this part. And now I need to do this. 10. And then I do its right subtree. But I do it in an in-order traversal, which means I do the left subtree, 12, then the root, then the right subtree, which does not exist. You start seeing a pattern here? It would be an ascending order. Gee, I wonder why we call it in-order traversal. Because it provides, with a binary search tree, it provides an in-order ordering of your elements. All right. Okay, great. Help me out here. Binary search tree. I've got the root. Remember, I've inherited the root. That's why I made it protected over here. All right. I've got the root because I do want to see it in the subclass here. I've got the root. That's one thing that I need. What else do I need though to create a binary tree? So with the integers, of course, that was natural. 2 comes before 10. 15 comes after 12, right? A comparator, private final comparator, right? And I'll just call it CMP. Right? Why do I need a comparator? Here's a node, right? Here's the key that I'm looking for. Is that it? Nope. Oh, okay, well, is it less? Yes. All right, go into the left subtree. Is it greater? Yep. Okay, then go into the right subtree. Right? I need a comparator to tell me all that stuff. Because I don't have integers here, I have t's. Right? Let me go ahead and create a public binary search tree constructor that takes a comparator for elements of type t. This.cmp equals to cmp. Right? Now I've got the two things I need. I've got a way of looking at what's in these two nodes and saying this node is greater than that node, and so it goes in that direction or that direction or whatever. And I've got the root. Right? Of course, I'm going to need to be able to put stuff in, right? For example, let's go back over here. Did I have an interface to add stuff to the binary tree? I just have a bunch of tree traversal strategies. I had to do all that manually here, right? So would it make sense? Public void add element. Element is of type T. You could do something like this. If it's just a binary tree, how do you add something? Well, could I search for it? I could do remember, this is just a binary tree now. Could I could do a preorder traversal, inorder traversal, et cetera, et cetera, et cetera, and I could search to see if it's in there, but that's all going to be order n because you're searching every element, and even then that doesn't give me a criteria for where do I put it? right? Oh, here's a leaf. Okay, make it its left child. Make it its right child. Or here's an open spot. Go ahead and put it there. That's good enough, right? So you could do that, but you have to define a strategy for doing it. I'm going to go ahead and do that in a binary tree, though. Right? Now, what's the strategy for doing this? Add the element. Actually, no, let's forget about add element. Let's search for element. Search for element. And we'll go ahead and make this into a Boolean. Let me rename this contains. Okay. Does it contain that element? True or false? Does this tree contain 49? True. Does this tree contain 42? False. Okay. And just to make sure that I'm testing it properly, I'm going to grab this. Okay. I don't have that tree. That's not a binary tree. So I'm going to have to create another binary tree. We won't test it today. I'm going to have a lot of work to do to set this same tree up over here. I probably have it somewhere. I'm not sure. Anyway, contains. Where do I start? I start at the root. Right. Now, let's search for it over here. Forget about the markup over here. I can get rid of all that. There's my current. I'm at the root. I'm going to ask, is this the thing that I'm looking for? Right? That'll take care of the root, right? If current dot get value is equal to that other element, right? And I'm not going to be able to do something like this, right? This is kind of pseudocodey. If the element stored or at the current node is equal to the element that you're searching for, in fact, let's call this needle, because I'm searching for the needle, right, in the haystack, then return true. Can I do that here, though? I mean, it's compiling, but it's compiling because same reason that if you have a string and another string and you used equals equals, it'll compile, but will it give you what you want? Nope. Even if it's hello and hello, it'll return false because those are two different strings. So what do I need? I need to use my comparator. Right? Compare, gotta spell it right, these two elements. And if the comparator says one thing or another, then I know that it's equal. How do I know if it's equal? If it returns 0. That works for the root, but does that work for searching for the rest of the entire thing? Nope. So I'm not going to have an if condition here. Well, I mean, I am ultimately, but I need to repeat this. Now I'm searching for 42. I start at the root. That's not what I'm looking for. Go to the left. That's not what I'm looking for. Go to the right. That's not what I'm looking for. Go to the left. Oh, it's not there. So I keep going until what? I've fallen off the edge of the tree. Right? So while my current node is not null, continue this process. If the current node is what I'm looking for, then immediately stop and return true. Okay? Otherwise, what do I need to do? So if the comparator tells me that it's less, right, that the current value is less than a needle, then where do I need to go? Current to, okay. If the current, which is 50, and I'm searching for 42, right? So 42, the needle is less than the current, go left, right? But is that the order that I have here? Let me go ahead and reorder them then, so make it really obvious. Right? And I'll put the needle first. Now, if the needle is less, so the same ordering, A, B, right? Now it's a little bit more obvious where to go. the needle, that you thing that you're searching for, is less than the current value, where do I go? Go left. Right. How do I go left? Current is equal to current dot get left child. Right. Else if, and I will go ahead and type it all out, even though it's not necessary here. If it's greater than 0, right, then that means that the needle is greater than the current, and so I go right. There. Once I've found what I'm looking for, I return true. Or once I've broken out of this loop, there is no 42. The current node is null. What should I return at the end? False. Now again, this if condition right here is not necessary because it's one, the other, or the third. So by process of elimination, you can go ahead and get rid of that. I'll go ahead and leave it in just to make it absolutely clear what we're doing here. So let's go ahead and create a very small tree here. Oops. I want the full main. Yeah, okay, main. Just to test it. It's a binary search tree. And let's say for integers. There we go. Ignore that. I need to give it a comparator. So a new comparator for integers. I think that there's one built in, but whatever. Add these methods. This is the old school way of doing it anyway. And then o1 dot compare to o2. There. Return that value. All right. That's going to sort them in ascending order, just like we did over here. Right. Now let's go ahead and test it by creating a couple of nodes. I'm just going to take this pattern over here. Let's put new tree node. This is going to be kind of arduous, I guess. 50. There. A is equal to our tree node. I don't know if this is worth it. I can do this offline. Integer tree node A is equal to 10. New tree node. I'll just go ahead and go with the first level here, 40. And then B will be 60. And then what I need to do is I need to construct it so that A is the left child of T of the root, and that B is the right child of the root. So T dot root dot left child. No. Set left child to A. T dot root dot set right child to B. And then we'll system dot out println T dot contains. Does it contain 50? This should be true, right? Yep, right there. This should be true. 60 should be true. Anything else should be false. Hey! Of course, I didn't take care of a whole bunch of other stuff, but you get the idea. No questions online. We'll go ahead and continue that on Tuesday, though.